Hi everyone, my name is Charlotte. Today I present you GlitchGlück. It's a guided hardware fault injection that will be able to trigger software vulnerabilities. So what are software vulnerabilities? Well, these are the bugs in the software logic that could be exploited to cause undefined processor state or undefined behaviors. And of course, there are software level countermeasures that could be able to protect them. For example, very simple example that the buffer overflow could be protected by input size validation. So buffer overflow is that when input data exceed the buffer size, and which will cause adjacent memory location to be overwritten, for example, the return address, therefore be able to take over the control flow. And input size validation will be simply just checking the input data before writing into the buffer. Well, with software level countermeasures intact, this could still be compromised by hardware fault injection. And one of the reasons is that the software level countermeasure is unaware of the hardware details. And what is hardware fault injection? Well, to use physical disturbance such as voltage glitches in the hardware to disrupt the intended circuit behavior that is designed by the software. For example, we have this input size validation in the behavior level, and of course, after compiling that, we have the assembly that also be able to visualize this software countermeasure. However, once we enter the gate level, these countermeasures will no longer be visible, and now everything is dissolved and decoded inside of the either modules or gates or registers. So then, if a hardware fault is injected using physical disturbance, that this could lead to a bottom-up fault propagation that would potentially initially cause a faulty bit in the register, and this could cause a faulty instruction that to be executed instead of a compare could be something else, and eventually the return address could be overwritten, even though within the software level countermeasure intact. Well, we all know that fault injections are so powerful, but there's also limitations on that. For example, the most traditional fault attacks were based on black box approach, meaning that we have very little visibility into the hardware details. We only know the inputs and outputs. And also, traditionally, we will adopt classic fault models such as instruction skipping. For example, we would assume that the compare instruction would not be executed, and then therefore the countermeasure would never be executed either. But this has been proven by other papers that these simple models were not enough to represent what exactly the complicated hardware details. People also use gate level modeling or also microarchitecture level modeling. Also, because of we're doing blind attacks, we need exhaustive fault parameter searches, such as thousands of trials need to identify just a very few meaningful fault effects. And also, very importantly, is that these attack methodologies is driven by your results. So therefore, it's based on trial and error approach, which is very difficult to conclude, and it's not easy to become portable. Of course, there are high-precision attack setups, such as low-cost laser or focus EM. It improves targeting, but still remain environment-dependent and non-portable. Well, for the attackers, large number of trials is okay because we could optimize the flow, but it's still, it's hard to conclude from the attack methodology. But for countermeasure designers, this is a disaster because for every single fault, we need to do a manual analysis to make sure that we could commit on this countermeasure. Well, so today I wanted to introduce you a guided hardware fault injection that is called GlitchGlück. And the biggest question coming is that, why do we need this guided hardware attack? Well, imagine that a thief is trying to steal a jewelry inside of a large building, and the thief has no idea about the floor plan of the building, where exactly the jewelry is located. Therefore, the thief is forced to have these blind guesses, open every single door. Of course, it's time-consuming, and it would also potentially trigger alarms. And we all know that by hearing of it, but the majority of the time, the thief will fail. And this, just like when we're conducting a fault injection without guidance, which is approaching like a blind process. But what if the thief has a very detailed blueprint of the building? Therefore, the building could no longer be a black box. We would be able to have the floor plan and to know exactly where the jewelry is located. Therefore, this blueprint has helped the thief to turn the guesswork into a targeted action. The thief will be able to create a plan which is faster and more accurate strategy to able to get the jewelry. And this is how we feel like when a fault injection with guidance, which is what I wanted to introduce of our paper. What we use is that we will use pre-silicon layout data as the blueprint, and in this case, we will have more accurate attacks, meaning that in the paper we could show by one single or two glitches, we'll be able to break the countermeasures. And in the designer side, we could also develop more stronger defenses. And there are two aspects of the GlitchGlück. The first one is the tooling aspect, that we will create and generate a novel data structure. And by having this data structure, we will be able to analyze the data structure and then use based on a guided methodology to complete the attack. So now let's go into the tooling aspect of GlitchGlück. Well, in the pre-silicon stage, how we generate the data structure to help attack is that first step is that we partition the hardware state into word level registers. We define the hardware state of the system as all the registers within the processor. And the reason why we chose processor only is because these registers in the processor, if faulted, could have the most immediate impact to trigger software vulnerabilities. So, and then we will use these register values to construct something called dynamic state transition graph. This is a novel data structure that you will be able to visualize, have a temporal visualization of how software-hardware interactions. Unlike static data structure like assembly or RTL, Verilog, we'll be able to have more interactive data structure that could present. And how exactly we do that? Very simple. We just document every single word level register output values, and these values are presented in hexamal inside of the node of the DSTG. So then we also have the edges of the DSTG that present at what clock cycle, what time that the value changes from one another. We also have simplified notations for recurring transitions just to reduce the plotting overhead. And now we'll be able to partition the entire hardware state into small pieces of word level registers, and for each register, it will have its unique DSTG plot. Well, this will be generated inside of the simulation test bench, meaning that no modification on RTL nor gate level. And of course, for larger DSTGs, we could simply choose the time window for plot and also what register to be plotted to reduce the overhead. And also, the DSTG is generated based on register output, meaning that any modeled effects, such as dynamic inputs that eventually will be clocked in, or simulated noise will be reflected in the flop as long as you can model that in a simulation. And of course, for unmodeled physical phenomena are not included unless you'll be able to model that and reflect it in the flop. Okay, so I'm going to walk you through a very, very simple example to go over the methodology. This example is the buffer overflow mitigation with input size validation using assert blocks. And we have just a simple walkthrough. We have the buffer size, which is 16 byte. The stream size is 19 byte, and then with a bunch of A's. And eventually, our target is to fault the return address of the main function. So I have another memory address here that I wanted to execute a malicious function, which it will do this. It is broken. Copy that into the memory allocation of 200. And of course, before copying, we will have this assert block here to check the size. And if it failed, then we will enter an infinite while loop. If it passes, then we will go ahead and execute the string copy instruction. So I wanted to use GlitchGlück to first generate the DSTGs, like what I've discussed in the 2 aspect, and then has a methodology that analyzes the DSTG and just use one single glitch to be able to break this countermeasure with minimal effort. So the methodology part of the first step is that we need to identify the vulnerable decision state. Well, this is a critical state that will influence the system behavior, representing a decision point in the execution flow, especially most of the time it will be located in a branch operation. And the key idea is that we need to manipulate the behavior at VDS through fault. Therefore, the execution path will change and lead to software vulnerabilities. Usually, we define the VDS inside of the program counter register. So let's see what does the DSTG PC tells us based on that small example. Okay, so we can see that at the node, there are some instructions that are being executed. We don't know what instruction, but there are instructions being executed. And we can also know that at what clock cycle this instruction be executed. Well, very interestingly is that you can see that there's a while loop happening at the end of the PC instruction, meaning that if I can see this, I know that my countermeasure is effective because it entered a while loop. And of course, I know that the string input size is larger than the buffer size. And this could be further validated by the assembly code that we can also locate that, well, this is where the while loop is being executed. And then remember, we wanted to identify VDS that this is a branch operation or execution decision point that would either go to the string copy function or enter in the while loop. So what we could do is we can trace back and where exactly this jump happens, either go to a string copy function or enter in a while loop. And then we can see, okay, F08E is where the decision occurs, either trigger the buffer overflow or not. So what we can do is that, okay, the VDS is located at instruction F08E. Once we have located the VDS, the next step is to determine the fault injection state. This is where the state that the fault is being injected, and it must have an immediate impact, dependency to the VDS. A single VDS may be associated with multiple fits, but usually the one that closer in time is always being selected. So we could further observe is that looking at the assembly, we know that, okay, what determines the jump instruction, the VDS, is that the compare instruction right before it, which is comparing R12 and R13. Well, as a traditional path, you could analyze this assembly going further and find out what exactly is being stored in R12 and R13. But you could also look at the DSTG of R12 and R13, and it would tell you exactly what are the values that are being compared right before the jump happens. These is exactly the attack string size and then the buffer size that are being compared inside of these two registers. So now, remember the goal is that to not take the jump and then go straight to the string copy instruction. So now I wanted to think about, well, can I use fault injection to make the value in R13 greater than R12, so therefore this jump will never be taken and it goes straight to the string copy instruction? Well, we'll be able to do that by one single glitch, and I think this is very interesting that it could only observe by the DSTG because we can see that the value at register R13 right before the value that is being compared is the hexamal value 213, which is being inserted before the 15 in the decimal in the buffer size. If we could fault the transition from 213 to F, therefore the value that eventually will be storing in the R13 will be greater than the value in the R12. So what we have decided is that, okay, we have located that the fault injection state is at register R13, and we wanted to fault the transition from 213 to F. Therefore, we will be able to locate a larger value at the time of the comparison, and then we can not jumping into the while loop. And the most importantly is that the next step is to establish the fault injection time. This is the exact clock cycle when the fault is being injected, because any random timing will not cause a direct impact that change the behavior in the VDS. Well, as previous slides knows that, we know that the DSTG will reflect the register output values, and also based on hardware knowledges, register input values, which is before the clock edge, that is being computed from the upstream logic and previous registers. Therefore, because we wanted to fault this transition, so the key idea is that the input value that loaded into the fits must be faulted. So we have this automated Python script that be able to parse the layout data, and then we have located that, okay, the transitions from 213 to F, the input values that is being toggling and being computed is at exactly clock cycle 923, which has 4 bits that are being flipped inside of the R13. And all of the bits has a maximal logic preparation time of 6 nanoseconds. Therefore, we could identify that the fault injection time is at clock cycle 923 with a logic preparation time 6 nanoseconds. All right, so we have all these 3 parameters. The next step is how we're going to use that to actually execute an attack. So what we wanted to do is to validate these attack parameters using simulation first. Well, depends on how you choose your attack methodologies, such as global fault injection, such as clock glitching. You could use these attack parameters differently than the localized fault injection. Well, if we're doing a clock glitching, then the glitch width must less than the logic preparation time, which was what we defined in the fit, because we wanted to interrupt the transition from 213 to F and result a value that is greater than F. And also, because of this is a global fault injection, therefore it could potentially fault other critical registers and let your processor enter an undesired state. Therefore, we partition the hardware state as well as automated Python script and be able to find out that all the critical register that could be able to stabilize with the logic preparation time inside of 4.7 nanoseconds. Therefore, any glitch width between 4.7 to 6 nanoseconds will be able to succeed the attack. For more localized fault injections, such as laser, we need to target specific bits that we wanted to flip in the fit inside of the R13. And by mimicking a physical attack of the laser injection, we do layout-aware laser injection. So I have a figure here that has the layout out of the die of the registers, and then with the register bits highlighted in the box. So what we do is that we will only choose a user available laser radius size. Therefore, any register within the radius size will conduct a bit flip in the simulation to mimic the post-silicon validation as much as possible. And so the fault simulation results that we validated is that we chose a 5 nanosecond clock glitch and be able to dump the memory content of at 200, and I see that ASCII string it is broken is showing there. That's how I know that attack is success. But this is not enough yet. We also need to do this post-silicon validation to validate our simulated fault parameters to complete the guided fault attacks. Well, we have the ASIC chip, in-house ASIC chip that we have the entire front-end, back-end, and then the chip with us. It's a very simple core OpenMSP430 with TSMC 180 nanometer, also with scan chain support. And we'll be using this scan chain to conduct the attack. I'm not going to go too much details on how exactly we execute the post-silicon. The paper here, you could, if you're interested, you could look into that and find out more instructions. But I wanted to discuss the results that we see. So the y-axis here are the clock glitch width that we executed on the post-silicon validation with ranging from 1 nanoseconds to 10 nanoseconds because we wanted to test our attack parameters. And the x-axis here are the R13 bits, which is scanned out after the fault is being injected by the scan chain. And we could see that with different clock glitch width, any glitch width that is greater than 6 nanoseconds, which is matched as the pre-silicon attack parameters, that the value inside of R13 did not change. But anything less than 6 nanometers will be able to result in a greater value in the R13, and then therefore the countermeasure has been bypassed. But any glitch of width that is less than 4.7 nanometers, we observe from the scan chain that there is also critical registers faulted and make that the processor enter an undesired state. So then it keeps stuck in a loop or not be able to complete the attack. And I really wanted to encourage you to read our other examples because what I have presented here is just a very simple example. But we also be able to do this fault simulation validation in different cores, IBEX and Pico RV32 with different examples. And then we'll also be able to perform like more than one glitches. And so it's very interesting and very strong to show you that it is very useful that how we be able to analyze the DSTG. And for conclusion, we introduced a novel data structure, DSTG, that be able to visualize, give a temporal visualization of the software-hardware interactions. And also, by having the DSTG, we could have execute this guided fault attacks without having a fault model assumption, which is very purely driven by the hardware data and details, and also portable between between examples. And by having this guided example attack, we avoid the blind attacks, and we'll be able to have very high precisions to reduce the fault parameter search space. And at the end, by incorporating with layout-aware fault simulation plus scan chain, we'll be able to validate our simulated results in the measurement on the fault experience. And for future work, well, we have a IBEX chip that is going to be taped out coming back this month with scan chain support, also including the memory modules that inside of the scan chain, so we have more visibility of what's going on for the whole chip. And we wanted to do more experiments on the post-silicon validations. Also, right now, the fault parameter extractions, the 3 steps are very manual. We need to analyze the DSTG, so we wanted to think of a way to do the automation and to make our methodology more robust. And these are my references on the slide. Thank you so much. If you have any questions.